Hello everyone, I'm very glad to share our recent work with you. The title of our work is Deep Stochastic Optimization for Algorithm-Specific Pilot Design in Massive MIMO. This is the outline of our presentation today. Now, let me introduce the first part. Due to the frequency division duplex dominance current wireless cellular systems, there is a significant commercial interest in enable FDD massive MIMO. To reduce the pilot overhead, compressive sensing-based channel estimation methods have been proposed by exploiting the fact that massive MIMO channels tend to be sparse in the angular domain. Most existing works on CS-based channel estimation have considered random pilots and cannot take advantage of the beforming gain. In practice, additional prior knowledge beyond the sparsity, such as channel statistics or angle of arrival of the users, can be exploited to optimize the pilot design in order to enhance the channel estimation performance. In this page, I list some related works. In reference 1, the authors use out-of-band spatial information to optimize the pilots. In reference 2, channel support side information is used, and in reference 3, an information theoretical approach is used. However, there are some advantages, such as they all use indirect performance metric, such as mutual information, to optimize the pilots, and there is a lack of closed-form performance analysis for a given iterative channel estimation algorithm. Some recent works attempt to adopt deep learning to solve the channel estimation problem in FDD massive MIMO. However, the deep learning approach has some disadvantages. First, it requires a huge amount of labeled data to train the deep neural network. Secondly, the success of deep learning relies on the assumption that the labeled data in the training stage have the same statistics as that in the online channel estimation stage, which is often not true in time-varying wireless channels. To overcome those drawbacks, we propose a deep stochastic optimization approach. In DSO, deep unrolling is used to construct a channel estimation neural network that models the massive MIMO downlink channel process, with a pilot acting as a weight in this network. Additionally, a model assistant online stochastic optimization method is used to optimize the pilots by training the CNN based on an online learned channel statistics model. Now, let me introduce the system model. Consider a massive MIMO system with one BS serving k single antenna users. The BS is equipped with M antennas. The received signal is given as follows. Due to limited number of scatters, the massive MIMO channel has a sparse representation under appropriate spaces D, and then the received signal model can be rewritten as a standard CS model. A proper probability model for the sparse channel X provides the foundation of exploiting the sparsity of massive MIMO channel. Moreover, in practice, it is possible to obtain some statistical prior support information. So we propose a three-layer theoretical Markov model to capture the statistical PSI and the channel sparsity, from which we derive a VBI-based channel estimation algorithm. In the proposed model, we introduce a support vector S, indicate whether the mth element of XM is active or inactive. Rho is a precision vector of X. The inverse of rho m denotes the variance of xm. Then we will arrive at the VBI channel estimation problems. In VBI, the approximate post-real is calculated by minimizing the KL divergence between the approximate post-real and the true post-real as follows. Solving the above optimization problem, the update equations of all variables are given as follows. Then, the pilot design can be formulated as the following weighted channel estimation MSE minimization problem. The VBI-based channel estimation can be viewed as a parameterized function, where the input is the received signal, the output is the estimated channel, and the function parameters are pilot matrix. One major challenge of solving P is that F involves an iterative channel estimation algorithm which cannot be expressed as a closed-form function of U. Moreover, the expectation operation further complicates the problem. To overcome this challenge, we propose a novel DSO approach. As illustrated by the two pictures, we use CNN to model the function where the input of the CNN is hk and nk. The output of the CNN is h hat k, and the CNN parameters are u. This CNN consists of a received generation layer that implements the received signal model, and the NN implements the VBI-based channel estimation algorithm via deep unrolling. The remaining question is how to obtain the training data. It is difficult to obtain sufficient channel samples due to the time-varying channel statistics for mobile users. Therefore, we propose a model-assisted online stochastic optimization method. The basic idea is to first learn a dynamic channel statistics model based on the past channel history, and then use the model to predict channel samples and train the CNN in an online fashion. The first part is a dynamic channel statistics model containing two parameters, the statistical channel support and the channel variance. The second part is a model-assisted online stochastic optimization problem of the CNN. The channel statistical parameters in the frame T can be obtained based on the estimated sparse channel vectors. Then, n-channel samples are generated according to the dynamic model and then used to optimize the weights of the CNN for frame T plus 1 via a standard stochastic optimization method. Finally, I will show our simulation results. We compare the normalized mean square error performance for the VBI-based channel estimation algorithm with random pilot, mutual information-based pilot design, and DSO-based pilot design respectively. In addition, we consider both a practical MSE estimator with learned channel estimation statistics and a generated MMSE estimator with perfect channel statistics information. From the first picture, it can be seen that the proposed VBI-based channel estimation algorithm with DSO-based pilot design achieves significant gain over both the MI-based and random pilot design. It is also outperforms the practical MLC estimator with MI-based pilot design. From the second picture, we can see the performance of both the MI-based pilot and the DSO-based pilot design decreases with the blockage probability. However, the performance of the DSO-based pilot design decreases at a slower speed. Moreover, the proposed scheme still outperforms all the practical baseline schemes and can even approach the performance of the generated MMSE estimator. This demonstrates that the proposed scheme can better adapt to the time-varying channel statistics. This is our conclusion. We propose a DSO approach for algorithm-specific pilot design in massive MIMO channel estimation. We first developed a VBI-based channel estimation algorithm, which can fully exploit the channel sparsity and the statistical PSI to approach the performance of the generated MSE estimator. Then, by combining deep unrolling and model-assisted online stochastic optimization, the proposed DSO can directly optimize the pilots to minimize the estimated MSE of the VBI-based channel estimation algorithm, without suffering from the high complexity and weak generalization ability of the deep learning approach. Simulation results verify the effectiveness of the proposed DSO-based pilot design. Here are some references. Thanks for your listening.